Chapter 10 is on sample surveys. Now, for this chapter, memorization is key. There'll be a lot of terms, so I suggest having note cards beside you, or a binder, or a notebook, something to write down these key terms and to work on memorizing and understanding the definitions. So let's start out with the basics right here. What is a population? Well, the population is the thing we want to understand. I always like to talk about somebody baking a cake, and you can think of the cake as something you would want to understand. So then how could you understand that cake? Well, you would take a sample of it. The problem with taking samples is sometimes we have biases in our sample. If you think about a biased way to take the sample, it would be to simply go across the top of it and just take some of the frosting. Now that's not representative of the cake if you just scrape off the top, so we have to watch out that we take a good representative sample of the thing we want to understand, which is the population. We can do this a lot of times by randomizing our samples, and we'll go over a lot of methods here on how to do random samples. So if we take an unbiased random sample, we should have an understanding of the parameter of interest. Now, what is a parameter? The parameter is the thing we want to understand. So if you want to understand how good the cake truly is, that is the parameter of interest. Your sample would give you a statistic, and this is where we get into the concept of inferential statistics. Inferential statistics means with your statistic, you try to infer the truth about the population. So statistics allow us to infer things about a population that is well defined, something we want to understand. Population, once again, the thing or people we want to understand. Parameter is going to be the truth. With this right here, you have examples of parameters down here at the bottom. What is the true GPA of all UT students who own iPads? Well, maybe we want to understand that and see what's going on. The only way to get an idea of that would be to take a sample of students who own an iPad at UT and then to try to infer what the truth might be. The better we do the sample, the better capability we have to infer the possible truth about the population. So what is that truth about the population? We keep saying it, it's the population parameter. Now, I do want to say sometimes people add extra words to this, like population parameter of interest, like population of interest. But the key word here, if someone says population parameter of interest, is simply going to be parameter. So it is for a population, but the parameter is the only thing we need to say, like, what is the parameter we're measuring? And it's just some quantity, and it's the quantity we want to understand for the population, as in all individuals. Like, what is the mean GPA of students who own an iPad? What is the true variation of their grades for students who own an iPad? What is the percent someone might get in an election? What percent of votes will they get on election day? Lots of other things could be the thing we want to understand. Think about the election one. When there's an election, there's a truth of what happens, but we can go out and do polling, which is sampling before the election, to try to infer what might happen on election day. And the less bias we have in our polling, the better representative sample we have, and the better we can make inferences about what will happen on election day. Once again, sample statistics are what we get from a sample. And if you hear sample statistics, that is just the key word, statistic. So one thing I like to say a lot is SSPP, because sample statistics allow us to infer population parameters. And once again, we keep saying once again here, but they have to be representative, because if you have junk sample statistics, you have junk over here, you get a junk estimate over here, and you don't want that. You want a good estimate that lets you infer what the truth might be for the population. Notation-wise, there's quite a bit of ways to write all this. Sample statistics have their own notation, and I like to think of small sample statistics. Most of them are small letters. It's not always, but most are small letters. And then Greek parameters. I like to say the Greek population parameters is the way I help keep it memorized, like the Greek population. It doesn't have anything to do with the Greek population, but if you think the Greek population parameters, you can remember that Greek letters, in most instances, point to it being a parameter, like mu, sigma, rho, beta, and that's just p right there. So it holds for most of these and helps us memorize them. The small sample statistics, we should know them also, like y bar is the sample mean of variable y. Standard deviation is S, which is sample standard deviation. Sometimes people put an X down here for a sample standard deviation of variable X, or it could be a y for sample standard deviation. It's a little subscript at that point. It's like below the variable itself. Sample standard deviation of variable y. With y bar, you can write x bar, and that is the mean of variable x, specifically from a sample. People even do things like mu sub x for the true mean of variable x. So once again, write these down and know how this sheet works with the combinations. Where if we had something like right here, sigma, what would sigma be? If you cross in on this, you can see sigma is the true standard deviation of a population. Sigma means you have all the data and you know the variation within the population. What about if we go to R? R came from a sample. We have sample data. We don't have all the data. And it's the correlation for a sample. So R would be said as sample correlation. So with that, write each of these down on a note card, know them, and understand when we use them. You've seen maybe a few for regression like B0, which is the estimate of the intercept, but beta 0 would be the true intercept. Like if we had all the data and we knew the intercept, that'd be beta 0. Proportion with the last ones down here. This is the proportion of a variable. And then we also have the true proportion. This is what you might get from a sample of what you think will happen on election day, and then this is what happens on election day. Conversely, with this, we have the complement, which we'll be talking about in the next lecture, which is Q hat. So if you believe your candidate's going to get 54% of the vote, that might be P hat. And this is from a sample. Q hat would be the vote they don't get, which is just this right here, 46%. So P hat and Q hat are complements. And then on election day, what truly happens, the true percent that happens, and the complement of that are P and Q respectively. A lot of good notation. Write it down, put it on note cards, and make sure to know these along with additional notation you might have learned. And we'll throw one or two more on here, like we have lowercase n and capital N right there, and that would be sample. So we have the sample size for a sample, or size, I should say, the size of a sample, the size of a population, lowercase n and capital N. Some good notation, write it down, helps with formulas. How large of a sample do we really need? Well, the biggest thing about the sample is not the size so much, but how we collect it. It makes the difference when we're talking about here, the size of the sample is going to make some difference, but it needs to be reasonably representative. That's our first goal, get a representative sample. And then the size of the population will not be used in a lot of our equations. The size of the sample kind of comes second after how do you collect your sample, how much do you get, and then the population size is rarely used in equations. Take, for example, the following equation, which you may have seen, would be p hat plus or minus z times, and we have here p hat q hat over n square root. And if you haven't seen this equation, hopefully you know the notation from the last slide. Notice that the only thing we're using right here is the sample size, and that's what's going to impact it. The population size is not used. It's the sample proportion plus or minus the z-score times the sample proportion and its complement over the sample size square rooted. So knowing your notation is going to come into huge help when you have to use a formula and you're reading through a question. Here we are in an example that it doesn't really matter on the size of the population. The size of the sample is what's going to matter right here. Once again, think about this in order. 1, how did you collect your sample? 2, what is the size of your sample is what would matter next. And 3, very, very way in the back, would be the size of the population. It does matter some, but you want to focus on how are you collecting your data, how much data are you collecting, and then you might think about what is the size of the population. Of course, all these things are going to be floating around in our head, but if you don't get a representative sample, you haven't done anything good. If you don't get a decent sample size, you probably can't make good inferences. And a lot of times with statistics, we're working with either a large or an infinite population, such as like basketball free throws or an election in the United States. Those would be infinite for basketball free throws and also extremely large for an election in the United States. So your estimates obtained from getting 1,000 observations would be the same, even with some pretty much advanced corrections that we use in advanced statistics. The sample frame, another key word we have right here, are the list of individuals or things you have access to take data from. Now be careful, this is not your sample. This is just everything you could theoretically sample. I like to ask students, if you stand outside the library at 3 p.m., here you are outside the library, and you're going to talk to people, what is your sample frame? And the sample frame would not be the students you get data on, that's your sample. The sample frame would be anyone within that area that you could possibly talk to. If someone is around the library around 3 p.m., they're in your sample frame because you could theoretically talk to them. So the idea of a sample frame is a theoretical idea and might be hard to even list every individual in a sample frame, but we often try to get an understanding of what our sample frame is. Maybe we take out a telephone book and we start flipping to random pages to call businesses to see if they use a certain service. And so we want to get the true proportion of businesses that use a certain service. We open up the page, we call that business. Any business in the telephone book is in your sample frame. All businesses that give you data or respond to your questions are in your sample. There's other things we'll talk about here soon, but these are the concepts you need to understand, because if we're doing this, let's define these terms. In that last example, the population would be all businesses. We want to understand all businesses. The sample frame would be the businesses in the telephone book that we have, because we could theoretically talk to any of them. The sample design is how we are doing this here, how we're drawing the data. It's just opening to a random page and calling a random business. The sample right here would be the businesses we talk to. Let's think about how we're going to collect these samples. We keep saying we do not want bias. Bias brings us away from the truth. So we want good, representative samples. What are some of the biases that can impact us? First off, voluntary response bias. And this is when people have a strong opinion on the survey. If you go out, especially with political topics, you might have people who really care about it and want to talk to you. You might be like, everyone cares about this topic so much. It's just because the people who don't care about it aren't talking to you. You might overrepresent the people with strong views in your survey. A lot of times, voluntary response bias creates kind of a distribution like this. Think about, when someone fills out a restaurant survey card asking if they enjoyed the food at the restaurant. Well, the people with a strong opinion are going to be the ones who love it or hate it. You're going to get people telling you those extreme polar opposites. You'll be like, well, no one has a decent experience. Well, they're the ones who are just like, meh, I'm not going to fill this out. So this is going to not let us understand the true experience at the restaurant, because the people who volunteer their experiences have more of a strong opinion, where the population that comes to our restaurant is not well represented by only the people with strong opinions. Some more voluntary response bias examples right there, but we'll go to the next one, convenience bias. Convenience bias is when you access the people or things that are easiest to get a hold of. What do? Well, maybe you need to do a survey for your class and you just post the survey online. Was that a good representation of maybe students at the University of Tennessee? No, you're probably getting a hold of your friends and people people within your circle of influence, and you might get opinions that are more closer to yours and be like, wow, everyone's just like me here. Well, it's because you did it in an easy way, and that's what convenience bias is when you collect your data in such an easy way, it doesn't get a good look at the population. So it's kind of limiting the way you collect data in such a way that you do it fast or quickly and don't properly take a look at the population. Posting surveys online, talking to the first 100 people you see. So those are good examples of convenience sampling. Just getting data really quickly is convenient. It's a bad way, it's biased, it doesn't get a good view of the population. Undercoverage might be a little more complicated, but don't worry, it makes sense if we think about it. It's when you don't get enough of a certain group or idea in a population. Let's say we were to go out and go to, let's say, Godiva chocolate. And we were to ask people, are you allergic to chocolate? Are you allergic? Do you have any reactions to it? And we talk to people in the store. That's a horrible way to collect data right there. And you might say, it's not really convenient because we're not like doing something easy. But you think about this. If you go out and talk to people in a candy store about candy, they're probably there to buy candy. And it's going to undercover people who are allergic to candy. And thus you don't get a true idea of what's going on. The US Census, even though it's called a census, does undercover homeless people, for instance. So when you think about this right here, they're not included. So if there was any views or issues or things we wanted to understand, the US Census is not going to cover those views, even though it's called a census and it's supposed to get the full population, because we are not getting data on that group. So when you think about it, imagine in your high school, You want to understand the views of all grade levels on how the education is at the high school. And you talk to students across all grade levels. It turns out the seniors are on, let's say it's senior skip day, and the seniors aren't at school. All of them have skipped. Well, then you don't get any seniors in your sample. So you've undercovered that group right there. Undercoverage is when you don't have enough of a certain group in your sample respective to that group's representation in the population. So think about, did I get enough of each view? We'll have ways to fix this here in a moment. Non-response bias, very simple one here. When people don't respond. Usually you get a telephone call, someone says, hey, I want to do a survey, and you say, nope. And in this instance, it's when their views differ from those who do respond. And I think a lot of times simply not responding is enough of a reason to say that you are somehow different from other individuals, because especially with telephone surveys, I don't take them anymore. My parents sometimes do. So now we're getting kind of under coverage a little bit because we're not getting younger people who might be more wary of telephone surveys due to our understanding of kind of scams. A lot of scams and stuff, sadly, influence people who are older, and maybe, because I grew up with this, we're more used to answering the phone and talking to people you didn't know. I get a call from someone I don't know nowadays, hang up or don't answer. So with this right here, you can see how we kind of some blending of the topics with non-response and undercoverage, where undercoverage is when you don't have enough of one group in your population, and non-response is when people are not responding and they somehow differ. Once again, the easiest way to think about non-response is simply people don't respond. You're outside doing a survey and you say, hey, would you like to do this survey? And someone says, no, they didn't do your survey. You tried to get data on them and they didn't respond. And in the worst instances, you might be holding a sign, supporting something, they see that sign, they're like, I don't want to talk about that. And that means that they hold views that maybe you are not getting. So the people who choose not to respond somehow differ in their opinions. And simply having a lot of people not respond probably means you're getting some non-response bias right there, and that needs to be looked into in your survey. Response bias, another easy one. This is when the bias is in the response. And this can be due to the way you word your questions, such as, do you think you're a good driver? A lot of people will say yes, and it's surprising, like 95% of people think they're a better driver than half the people on the road. Well, that's impossible. We'd have to look at better ways of collecting this data, a better way of understanding it. One of my favorite ways to phrase things is, and this is just giving you an example of response bias that I'm trying to elicit from you, is do you think it's fair that at 18 you could go to war, own a home, get married, have a kid, have a dog, but you can't buy a beer? Do you think that's fair? Do you think we should change the legal drinking age? All of that stuff beforehand is not meant to be part of a question. That's all pushing somebody towards an opinion, trying to get a response from them, biasing the response in your direction. So in this instance, we would say the surveyor put response bias into the question. We should just ask people, what do you think the legal drinking age in the United States should be? We should say it just like that. We as people who do surveys should not input our own bias into this, because we want to understand the views of individuals and not push our views into the survey and then see those views in the results. How can we get better surveys? Well, here are the methods. Make sure once again to have your note cards out and write down these methods. Simple, random sample. Write down the steps right here. Step number 1, everything in the population gets a number. Kind of technically, you could have student IDs, which are kind of enumerated, and then you select something randomly. That's all it is. Everything gets a number, everything gets an equal likely chance of being selected, and then we just select. 1, everything gets a number or ID. 2, select the numbers or IDs randomly. And think about this. That means everything has an equal and likely chance to be selected, and that's kind of key right there. In simple random sample, everything has an equal and likely chance of being selected, so you shouldn't undercover things, you shouldn't be biased. Now, you can't stop things like non-response bias, and you gotta look at how you write your questions, but this would guard against things like undercoverage bias right here. Next, we have systematic sampling, and the key word right here is every kth. Now, kth is just a placeholder for something like every 5th, every 10th, every 100th, it depends. And you have to think about how you're collecting this data, because maybe you're crash testing cars and you want to know, do we have reason to believe that there is a danger with our car? Well, let's crash test every second car. You can do second, you have to change the wording. We're going to destroy 50% of your product then. It might not be how companies want to do that. You might crash test every 100th car. I don't work in car construction or car manufacturing, obviously. And I don't know if every 100th would be a good standard, but you might want to literally put it through a bunch of tests and make sure you meet standards. Now, a problem with this is going to be maybe there's something in the production line of every 100th car that maybe is towards the end of the day. So you have to watch out for a systematic error in this process. But all you do is one, choose a random starting point in your process. Say, okay, we're going to figure out a random number here. Random number generator says start at 34. And then you would sample number 34, number 134, number 234, number 344, 444. And then you could technically start the next day by generating another new random number to start on that day and start crash testing those cars. And this is how we try to take a random sample right here. And it's also more organized. It's easier to remember which one to go to. Because you don't have to keep generating random numbers and say, okay, wait a minute, it said crash test car 18 today. Now, one thing I guess if we're crash testing cars is we have to be careful that the people don't know which cars we're doing, because maybe they'll try to make sure those cars meet certain standards, because they could start to get biased in some way and try to push it to look like better cars. Be like, oh, this is one of those crash test cars. Better make sure it's really good. You really have to watch out when taking data. You might want to, what we say, blind people to what is being done and not let them know which cars are being sampled. Blinding means they do not know about the process by which we are doing, and they wouldn't be able to influence it in some way. Next, we have stratified. This is where people usually get confused. The key thing about stratifying is we acknowledge a difference in the population and then sample according to that difference. We acknowledge a difference within the population and then sample in accordance to that difference. That's the key phrase. What does that mean? Maybe we want to understand the freshmen, sophomore, juniors, seniors at our high school. With that in mind, each class is of equal size. We want 100 students in our sample. So we sample 25 freshmen, 25 sophomores, 25 juniors, 25 seniors. We've now stratified by class. And within each class, we take a simple random sample where we just simply randomly select individuals within that group. And once again, stratifying starts by acknowledging a difference and then sampling according to that difference. Do a simple random sample within the difference. Maybe we have flights on an airplane and we're looking at the domestic flights and the international flights. There's the issue. Our airline has about 20% international flights and 80% domestic flights. So think about this. If there's 20% international and 80% domestic, and we want to take 1,000 airline passengers to understand their views, how many domestic passengers would we take? We would take 800 because that's representative. So we have 1,000 passengers we want to understand. 80% of all the flights we do are domestic. 80% of 1,000. So now we've properly represented them due to their size in the population. Once again, stratified is really going to help us guard against undercovering, because people can't say, well, you only got the views of domestic. We're like, well, no, they're 80% of the population. So we took 80% of our sample as domestic to be representative of their amount in the population. With other examples right here, or other topics, we have cluster samples. This is why people get confused, because it also deals with groups. The point of cluster sampling is to make sampling easier. We can go back to the airline. We would not cluster sample on international and domestic, because when you cluster sample the groups, you take all individuals in the group and you do a census on the clusters. Look at the keywords right there. We could, however, cluster sample flights. We could have someone go onto the flight before it takes off and say, hi, we have these surveys for you right here. If you could fill these out, we'd really appreciate that. Imagine everyone fills it out. We don't get any non-response bias. So they're doing a census of that plane, a census of that cluster. And so instead of trying to get individual passengers, we take one flight. Now, the flight should be thought of as kind of a random sample of our passengers. It's not perfect. I know it's not an international domestic flight, or it could be one that is going domestic and then going international, so we might have a good mix. We could pick flights like that. Then we got to watch out, because now we're picking a certain type of flight. We have to make sure we are representative of the people who fly on our plane. We can think about Neyland Stadium right here at the University of Tennessee, and maybe we want someone to go and survey people to ask them if they are enjoying the football game. Well, you could go to a row of people and talk to everyone in that row. That would be a cluster, and you would just take random rows around the stadium and say, go to this row, And if we took random rows, we'd get some that are close, some that are far away, and we'd probably get a representative sample. And that's easier than saying go to this person in this seat, this person in this seat. You'd get your sample a lot faster. Please understand the key differences right here. Clustering is like taking a whole bunch at once very quickly and sampling all of them. Where stratified acknowledges differences and then randomly samples within those differences. Write those down right there. Cluster sample has things in groups and then takes a census of the groups. Stratified acknowledges the differences by which we will do random samples within those groups. And last but not least, we have multi-stage sampling. Multi-stage sampling is any of these put together. So one of my favorite examples right here to do a multi-stage with is to say we want to talk to University of Tennessee students and we want to see their views on living in the dorms. Now you have to talk to students in the dorms. That's our population interest. We want to say, do you enjoy it? That's the parameter of interest we're looking at. And with this, we want to take a sample right here and we think about how we're going to do it. We go and we say, let's go to each dorm and take only 20% of the floors. So if a dorm has 10 floors, it's a big dorm, we're going to take 2 floors. And we'll round up if needed, because if a dorm has 7 floors, we'll take 2 floors, we'll round up. If a dorm only has 3 floors, we'll take 1 floor, and we'll talk to everyone on that floor. What method is being used? Well, the floors, did you hear I said we'll take everyone on the floors? If we're taking everyone on the floor is a cluster. We're speaking to everyone on the floor. The dorm's not a cluster. We're not talking to everyone in the dorm. And then we're trying to do it representative by each dorm. Like the dorms, we're trying to represent them properly by taking percentages based on floors. Like, okay, if it has 3 floors, we'll take 1. If it has 7 floors, we'll take 2 floors. We're trying to do it representative to how many people are in the dorm. Well, that's the stratifying. And then we are not doing a simple random sample. And because we're not doing a simple random sample of the stratas, that makes it a multi-stage. It is a multi-stage 2-step where we're first stratifying by dorm and then cluster sampling within the dorms by floors. What about if we were to go to the dining hall here on the University of Tennessee and we were to ask people their views on dining hall food? We've got to be careful because that's not all University of Tennessee students. It's students who eat at the dining hall now. And it's also at a particular time. So we got to look at it the way we're doing our sample frame. Might not be perfect, but we'll go with the example for now. We go around and we talk to every 5th table that we see and talk to everyone at it. We just start counting 1, 2, 3, 4, 5 and sample that table. 1, 2, 3, 4, 5, sample that table. So what are we doing? Well, we are doing a systematic cluster because cluster usually randomly picks the clusters. Usually a cluster will be that we just have things in groups and we randomly select different clusters. Systematic says every something observation, every 5th, we can put right here, every 5th observation we'd pick from a random table and then select every 5th random table going forward. So the idea of every 5th is systematic, and then the idea of talking to everyone at the table, not just an individual, is taking a cluster because we're just taking a whole bunch at once to speed up the process. See if you can write down some examples, bring them to class if you have a class, and good work, keep it up, have those note cards ready. Bye for now.